Hey, we're on to 7.6, which is function notation. We all know what this looks like from our calculators. It's this idea that when I have a function, I got an ordered pair. Y is a value of the function of x. We might write this that y equals f of x. Some examples of that, if we had our y equals mx plus b, the slope-intercept form of the equation, that would be written as f of x equals mx plus b. This is function notation. Let's go play with it. Given a function with equation f of x equals a negative 3x minus 1, find f of 3. So f of 3, which is how we say it, is the function where we define the x value and the function has a value given that x. So f of 3 equals a negative 3 times x, which we've defined as 3, times 3, minus 1. This is f of 3 for f of x equals a negative 3x minus 1. F of 3 equals a negative 3 times 3 minus 1. That sure looks to me like that would be a negative 9 minus 1. So f of 3 equals a negative 10. This is our application of function notation. Okay, we're on to guided example 2. We're going to use the three functions discussed at the beginning of the lesson on page 432, where e is the exponential growth, L is the linear growth, and C is the constant situation where it's just simply the same all the time. And we want to write these in using function notation. We can determine a new value for this. So for e of x, for 100,000 times 1.02 raised to the x power, then e of 10 becomes 100,000 times 1.02 raised to the 10th power. After 10 years, the population based on the exponential model is predicted to be about, you need to do this calculation, 100,000 times 1.02 raised to the 10th power. And that should give you an answer of around 121,899 peeps. Our linear function means that it just grows the same each year. So 100,000 plus 3,000 times x. So it'll be 100,000 plus 3,000 times x, which is 10, and our result for that calculation will be that we're at 130,000 people after 10 years. The constant one after 10 years should be pretty clear because it's after 10 years the population based on the constant model, is predicted to be 100,000 people. So no change because it'll be constant throughout. So here's an example of using our function notation to arrive at a conclusion based on some problems we saw earlier. And it's just kind of redefining how we express these. More function notation. Here's example 2. Use the three functions given earlier for population model to find what e to the 15, L to the 15, and c to the 15 are. Explain what the results mean in the context of the population situation. Well, remember, e was the exponential function, and the exponential function was, e to the x equals 100,000 times 1.02 to the x. Since we want e of 15, we write e of 15, and that's 100,000 times 1.02 raised to the 15th power. So that's our 2% growth model, and we want to know what that equals, so run the calculation, and we would see that using this model, the function of e to the 15, then e of 15, would give us about 134,587 people. Our linear model for linear growth is, again, we would write this to begin with as L of x equals 1,000 plus, and our growth factor for that linear function was 3,000 times x. We rewrite this using L of 15, and L of 15 gives us 100,000 plus 3,000 times 15, and that equals 145,000 people. And last, c of x, the constant of x is 100,000. Since there's no x value, c of 15 is equal to 100,000. Now, what does this all mean? It says, explain what the results mean in the context of the population situation. Explain means, in the English language, using complete sentences, say what it means. For this one, after 15 years, the population is 134,587. That would be a good way to describe it. For the linear model, we could say that after 15 years, the population predicted by the model is equal to 145,000. And for the constant function, we could say that after 15 years, the population based on the constant model is predicted to be the same, or 100,000 people. Let's take a look at example 3. Possibility 2, use the linear function L of x equals 100,000 plus 3,000x to model the population of a town x years in the future. According to this model, in how many years will the population reach 170,000? Well, this is our linear model, and so what we're now asking is, what we don't know what x is. It's asking for how many years, so we're saying that L of x, equals 170,000. And what was the original function? The original function was 100,000 plus 3,000 x. So now we want to solve for x, so I think first I'm going to subtract 100,000 from both sides, and I'll get, when I do that, 70,000 equals 3,000 x. Next, I'll multiply both sides of the equation by 1 over 3,000. Three thousands are going to cancel. I'm going to be left with x, and I want to know what 70,000 divided by 3,000 is, and I get that it is basically 23 and a third, or 23 repeating, or we can just simply go with 23 as they do up here. But 23.3 repeating would be a decent enough response for that. So that's in how many years this will occur. It's simply identifying, we know what the function equals, we now solve for that, find our value of x. For the exponential model, where e of x is equal to 100,000 times 1.02 raised to the x, it asks you to use the graph to find when the population reaches 200,000. Well, if we were to graph this, we want to know at 200,000, you'll notice this is population in thousands, so this is 200,000. I draw a horizontal line, and I look for where does the exponential function cross it. I could graph these on the graphing calculator and put the results in and trace it and find the intersection of the two. And from there I'd say when p is equal to 200,000 and when p equals 200,000 for our calculation is where these two cross, I'm going to drop my line down from this point, and I'm going to see that I'm close to, I'd say, 35 years from now. Okay, that's it for this lesson. Not a lot to talk about, a bit of practice, so work through it. Remember to write things out. If you're puzzled, write things down so you can take a look at it. Don't just let it rattle around in your head. Give yourself a chance to succeed with it. Best of luck. See you in class. Bring your questions. Good luck on the mastery quiz.